You know, there's something deeply wrong with the universe. I mean, fundamentally, mathematically, completely wrong. And the fact that you're sitting there listening to this, that I existed to say these words, that stars shine and planets orbit and anything exists at all, well, that's the puzzle. Because according to our best theories, the most precise equations we've ever written down, none of this should be here. Nothing. No galaxies, no atoms, no you, no me. Just empty space filled with light. Let me explain what I mean. When we look at the equations that describe how particles behave, when we write down the mathematics of quantum field theory, and we apply something called CPT symmetry, we discover something extraordinary and terrible. For every particle that exists, there must exist an antiparticle. For every electron with negative charge spinning one way, there must be a positron with positive charge. For every proton, an antiproton. For every neutron, an antineutron. Now, this isn't just speculation or philosophy. We've made antimatter in our laboratories. We've watched it annihilate with regular matter in our particle accelerators. When an electron meets a positron, they don't bounce off each other. They don't combine into something new. They completely destroy each other and turn into pure energy, into photons, into light. Einstein's equation, energy equals mass times the speed of light squared. It works both ways. Matter can become energy, and energy can become matter and antimatter in exactly equal amounts. So here's the problem. At the beginning of the universe, at the Big Bang, we had pure energy, enormous amounts of it, concentrated in an unimaginably small space. As the universe expanded and cooled, that energy started converting into particles. But the laws of physics, our equations, they're completely symmetric. When you make an electron, you must make a positron. When you make a quark, you must make an antiquark. The laws don't prefer one over the other. They can't. That would violate charge conservation, CPT symmetry, all the fundamental principles that we've tested billions of times in our experiments. So in the early universe, for every fraction of a second after the Big Bang, we should have created exactly equal amounts of matter and antimatter. Exactly equal. And then what happens? Well, as the universe expands and cools, eventually these particles start running into each other. Every electron finds a positron. Every proton finds an antiproton. They annihilate. They turn back into light. And at the end, after all the matter has found all the antimatter and destroyed itself, you should be left with nothing but photons. A universe full of light and absolutely nothing else. No atoms, no molecules, no stars, no planets, no people to wonder about any of this. But look around. Here we are. The universe is full of matter. You're made of matter. The chair you're sitting on is matter. The earth is matter. The sun is matter. When we look out into space with our telescopes, we see galaxies made of matter, not antimatter. We can tell the difference, by the way. If there were antimatter galaxies out there, we'd see the signature of annihilation. At the boundaries where matter and antimatter regions meet, we'd see enormous amounts of gamma rays with very specific energies, the kind you get when protons and antiprotons destroy each other. We don't see that. The universe, as far as we can tell, is made almost entirely of matter, with essentially no antimatter anywhere, except the tiny amounts we create in particle collisions or that come from cosmic rays. Now let me be very precise about this asymmetry because the numbers are staggering. When we look at the cosmic microwave background radiation, that ancient light left over from when the universe was only 380,000 years old, we can count the photons. There are a lot of them, about 400 photons in every cubic centimeter of space. And when we count the protons and neutrons, the matter particles, we find about one matter particle for every billion photons. That's the ratio. 1 in a billion. Now think about what that means. In the early universe, there must have been 1,000,001 matter particles for every billion antimatter particles. Just one extra matter particle for every billion pairs. All the billion pairs annihilated into photons. That's where those 400 photons per cubic centimeter came from. And that one leftover matter particle out of every 1,000,001,000, that's us. That's everything we see. Every atom in your body, every star in the sky, every galaxy in the observable universe, were all the leftovers from an almost perfect symmetry that was just barely imperfect. So the question becomes, why? Why was there one extra matter particle for every billion? Where did that asymmetry come from? This isn't a small problem. This isn't some minor detail we haven't figured out yet. This is fundamental. If the universe started perfectly symmetric and our laws of physics are symmetric, how did we end up so asymmetric? Now, I have to tell you something about how physics works. We don't like to just say, well, maybe it started that way. Maybe the initial conditions of the Big Bang just happened to have slightly more matter than antimatter. That feels like cheating. That's not an explanation. That's just pushing the question back one step. Why would the initial conditions be asymmetric if the laws are symmetric? And besides, we've learned to be very suspicious of initial condition explanations. Usually when we think we need special initial conditions to explain something, it means we're missing some dynamical process, some physical mechanism that naturally produces what we see. So we need a process. We need some physical mechanism during the early universe that could create more matter than antimatter, even though the laws of physics seem to treat them equally. Now, this seems impossible, right? How can symmetric laws produce an asymmetric outcome? But here's where it gets interesting. In 1967, a physicist named Andrei Sakharov figured out what conditions would need to be true for such a process to work. He came up with 3 requirements, 3 things that must all be true simultaneously for the universe to generate more matter than antimatter. First condition, there must be processes that violate baryon number conservation. Now, what does that mean? A baryon is a particle made of 3 quarks, like a proton or a neutron. Baryon number is just a counting system. We assign a baryon number of +1 to every proton and neutron, -1 to every antiproton and antineutron. In all the processes we normally see, baryon number is conserved. If you start with 2 protons, you end with 2 protons worth of baryon number, even if they've changed into other particles. But Sakharov said if you want to create more matter than antimatter, you need processes where baryon number isn't conserved. You need reactions where you can start with 0 baryons and end up with a net positive baryon number. Second condition, you need C and CP violation. Now this is subtle. C stands for charge conjugation. It's the operation where you swap every particle with its antiparticle. CP adds in another operation called parity, which is like looking at things in a mirror. For a long time we thought the laws of physics were perfectly symmetric under C and under CP. We thought that if you took any physical process and swapped all particles for antiparticles, or if you did that and also looked at it in a mirror, you'd get another perfectly valid process that happens at exactly the same rate. But in the 1960s, we discovered that CP is actually violated in certain rare processes involving particles called kaons. Later, we found it in B mesons, too. The amount of violation is tiny, but it's real. Nature does distinguish between matter and antimatter in subtle ways. Third condition, you need the universe to be out of thermal equilibrium. This one is crucial. If the universe is in thermal equilibrium, then even if you have processes that can create a matter-antimatter asymmetry, the reverse processes will happen at exactly the same rate and undo everything. Equilibrium means everything is balanced. But in the early universe, as it's expanding and cooling rapidly, things are not in equilibrium. Reaction rates can't keep up with the expansion. Particles fall out of equilibrium. And during those out of equilibrium moments, if you have baryon number violating processes with CP violation, you can create a net matter asymmetry. Now here's what's both beautiful and frustrating. We know all 3 of Sakharov's conditions are satisfied in nature. We know baryon number violation exists in certain theories that extend the standard model. We know CP violation exists because we've measured it. We know the early universe was expanding and cooling, so it was definitely out of equilibrium. The conditions are there. The possibility exists. But when we actually try to calculate how much matter-antimatter asymmetry should be produced using the CP violation we've measured in the standard model, we get a number that's way too small. Orders of magnitude too small. The CP violation we've discovered just isn't strong enough to explain why 1 in every billion particle pairs survived. So we're stuck. We know the mechanism that must have operated. We know it requires these 3 ingredients. We know nature provides all 3 ingredients, but we don't know the details. We don't know exactly which processes in the early universe were responsible. There are theories, lots of them. Grand unified theories that unify the forces at very high energies predict baryon number violation. Some versions of supersymmetry predict additional sources of CP violation. There's a mechanism called leptogenesis that creates an asymmetry in leptons, particles like electrons and neutrinos, and then converts that into a baryon asymmetry through other processes. There's even speculation about processes during cosmic inflation, the rapid expansion in the first fraction of a second that might have seeded the asymmetry. But here's the thing, we don't know which of these is right. We haven't seen the particles or the processes that would tell us. We're in this frustrating position where we understand the principle of what must have happened, but we don't know the specific physics. It's like knowing that something must have caused the explosion, and knowing it requires fuel and oxygen and ignition, but not knowing whether it was gasoline or dynamite or something else entirely. Let me put this in perspective. The Standard Model of particle physics is the most successful scientific theory ever written. We've tested it in millions of experiments. We've verified its predictions to absurd levels of precision. We predicted the masses of particles before we found them. We predicted the existence of the Higgs boson decades before we discovered it. The theory works, but it cannot explain why you exist. It cannot explain why there's matter in the universe instead of nothing. That one particle in a billion that survived that we're all made of, the Standard Model gives the wrong answer about where it came from. Now, some people hear this and they get nervous. They think, oh, physics must be all wrong then. But that's not what this means. The Standard Model isn't wrong. It's incomplete. There's a difference. The equations we have are correct for everything we can test, but they're not the whole story. There's physics beyond the Standard Model, physics at higher energies or involving particles we haven't discovered yet, that fills in the missing pieces. And this is why we build bigger particle accelerators. This is why we spend billions of dollars smashing protons together at the Large Hadron Collider. We're looking for those missing pieces. We're looking for new particles that could provide stronger CP violation. We're looking for evidence of baryon number violation. We're looking for any hint of what physics operates at energies we can't quite reach yet, but which were common in the early universe. There's also something philosophically profound here that I want to point out. The question isn't really why does matter exist? Matter and antimatter are on equal footing in our equations. The real question is why does anything exist at all instead of pure energy? Why didn't the universe just stay as photons? And the answer is, there was a tiny imperfection, a tiny asymmetry, just one part in a billion. That's all it took. That tiny deviation from perfect symmetry is the reason for everything. Every atom, every molecule, every structure in the universe exists because of an imperfection. You know, we often think of the laws of physics as describing a perfect, symmetric, beautiful mathematical structure, and they are beautiful. The symmetries in our equations are gorgeous. But the universe we actually live in isn't perfectly symmetric. It's slightly broken. And that breaking, those small violations of symmetry, they're not bugs in the system. They're features. They're what makes complex structure possible. Perfect symmetry would be sterile. Perfect matter-antimatter symmetry would be a universe of pure light with no structure at all. We exist because the universe is imperfect. Now let me tell you about another way to think about this problem because I think it's illuminating. Imagine you have 1 billion pairs of gloves, left and right, and you have one extra left glove. Now you throw all the gloves in a big box and shake it up. A perfectly symmetric process, right? The shaking doesn't prefer left or right, but when you're done, you reach in and pull out gloves at random, matching left with right, and throwing away the pairs. Eventually, you've gone through all billion pairs, and you're left with one left glove. That one left glove isn't there because the shaking preferred left over right. It's there because you started with an asymmetry. But now imagine a different scenario. Imagine the gloves are unstable. Imagine that under certain conditions, a right glove can occasionally transform into a left glove, and vice versa. And imagine that this transformation happens slightly more often in one direction than the other. Not much, just 1% more often left to right than right to left. And imagine this transformation can only happen when the temperature is in a certain range and the box is cooling down, passing through that temperature range quickly, so the gloves don't have time to equilibrate. Now you start with equal numbers of left and right gloves, but after the box cools through that special temperature range, you end up with slightly more right gloves than left. That's more like what we think happened in the early universe. The asymmetry wasn't baked into the initial conditions. It was generated dynamically by processes that treated matter and antimatter almost the same, but not quite, operating during a window of time when the universe was out of equilibrium. And that tiny difference, amplified over billions and billions of particles, gave us the matter-antimatter asymmetry we observe. But here's what keeps me up at night. We're talking about processes that happened when the universe was less than a second old, maybe less than a microsecond old. Energies and temperatures we can barely imagine, let alone recreate in our laboratories. We're trying to reconstruct what happened during that time using the traces left behind, like detectives arriving at a crime scene billions of years after the fact. We have clues. We have the cosmic microwave background. the abundances of elements, the matter-antimatter ratio. But we're missing the direct evidence. We haven't seen the particles or forces that drove the asymmetry. And there's another possibility I should mention. Though it seems less likely, maybe the universe is actually symmetric after all, just on a larger scale than we can see. Maybe there are regions of antimatter out there, enormous domains of antimatter galaxies, separated from us by vast voids where matter and antimatter have already annihilated. If those domains are far enough away, beyond our observable horizon, we'd never see them. We'd think the universe is all matter just because our local region is all matter, but this seems contrived. Why would matter and antimatter segregate into such large domains? And we still don't see the annihilation radiation we'd expect from the boundaries, even from relatively nearby antimatter regions if they existed. No, I think the universe really is asymmetric. I think there really is almost no antimatter except what we create or what's created in high-energy collisions. And I think that asymmetry was generated in the early universe by processes we don't fully understand yet, but which must obey Sakharov's three conditions. The beautiful thing is we're not stuck just theorizing. There are experiments we can do. We can study CP violation in more detail, looking at more types of particles, measuring it more precisely. We can search for proton decay, which would be evidence of baryon number violation. We can study neutrinos, which might play a role in leptogenesis. We can look for new particles at higher energies. Every piece of data constrains the possible explanations, narrows down what could have happened. And maybe someday, maybe in your lifetime, we'll crack it. We'll discover the new physics that explains the asymmetry. We'll find the particles or forces that were responsible. We'll calculate from first principles why the ratio is 1 in a billion and not 1 in a trillion or 1 in a million. That would be something. That would be understanding where we came from at the deepest possible level. But even if we don't figure it out completely, even if the details remain mysterious, we already understand something profound. We understand that our existence depends on an imperfection, a breaking of symmetry, a tiny violation of what seemed like a fundamental law. We understand that the universe could have been empty, should have been empty according to our best theories, but isn't. And we understand that figuring out why not is one of the great outstanding puzzles in all of physics. You know, people sometimes ask me if these kinds of questions matter. Why do we care about matter and antimatter in the early universe? What difference does it make to everyday life? And the answer is, it makes no difference at all to everyday life, and it makes all the difference in the world. You don't need to know where the matter-antimatter asymmetry came from to build a bridge or cure a disease, or even to build computers and smartphones. But if you want to understand the universe, if you want to know why there's something rather than nothing, if you want to grasp the deepest principles that govern reality, then these questions matter enormously. They're the questions that define us as a species, that separate us from just surviving to actually understanding. And there's something wonderfully human about this pursuit. We're matter, temporary arrangements of atoms that somehow became conscious, and we're using that consciousness to figure out why we exist at all. We're asking where the atoms came from. We're reconstructing the first moments of the universe, times and places we can never visit, using mathematics and experiments and careful reasoning. That's extraordinary when you think about it. So here's where we are. The universe should not exist, not in any form that includes us. The laws of physics, as we understand them, predict a sterile cosmos of pure light. But the universe does exist, full of matter and structure and complexity. Somewhere in the first moments of cosmic history, something happened. Some process operating under conditions of extreme energy, with baryon number violation and CP violation, and far from equilibrium, tipped the balance, 1 part in a billion. That's all it took. And from that tiny excess, everything else followed. The first atoms, the first stars, the galaxies, the planets, chemistry, biology, consciousness, you and me having this conversation. We don't know exactly what that process was. Not yet. But we know it must have happened. And we know, roughly, what ingredients it needed. And we're looking for it in our particle accelerators and in our equations and in the ancient light from the early universe. And maybe we'll find it. And when we do, we'll understand one of the deepest mysteries of existence. Why is there something rather than nothing? Because the universe is imperfect, broken just enough to be interesting, asymmetric just enough to allow complexity, to allow stars and planets and people who can wonder about their own origins. That's where we are. That's the puzzle. The universe should not exist. But here we are anyway, trying to figure out why.